Okay, so last lesson, all we were doing was integrating single terms. So just say we had x to the 3 plus 2x plus 5. What we were doing was just using that rule to increase the power and divide by the power. So it's fairly algebraic. So the antiderivative of this will be x to the 4 on 4 plus x becomes x to the 2 on 2, and the 2's cancel out, so that's going to be x to the 2 plus 5x plus c. All right. Now, what if we were to antiderive something that looked like this? Well, a simple way to do it, so if f of x was x plus 2 all cubed, we could expand that binomial or just using the algebraic technique. But like that's time consuming. Don't really like expanding cubics, to be honest. And what if it was power 4? What if it was power 10? What if it was power 54? No way I'm going to expand it into single terms and use this technique. So conveniently, there's a rule that explains how to do this move here, and it's on your formula sheet. That's it there. And it's fairly easy to sort of see what it's telling you to do. That n goes to n plus 1, that a goes to there, and we multiply that a value by n plus 1. We do 1 over that value, and we're only allowed to use it for situations where n is not equal to 1. All right, but I don't love rules and I like to know what's happening. So I'm not going to use the rule for these examples. You can use it, feel free to, but I'm going to use a u substitution. Okay, so why am I going to do that technique? Well, one, I can do it without the formula. Okay, two, I sort of understand a little bit more about how the parts are coming out. And three, it's something that we can use later on when we integrate special cases. And it also is used in some further calculus courses, I think from memory, integration by parts and things like that. So let's have a look at how it works for a couple of examples. So find the antiderivative of this. Let's do it. Okay, so again, your option at this stage is to expand that out, okay, which is really time consuming. And if you're like me, I just can't do a cube expansion without stuffing up somewhere. So what's our technique? Well, we're going to do a u substitution. So I'm going to say that this is actually the same as u to the 3, where u is equal to 2x takes 7. All right, now notice our variable here. If we want to integrate this, this is for the independent variable u. This can't be a dx anymore. It has to be a du if we want to integrate it or anti-diff it. So what do I need to do? Well, I'm just going to do this, see what happens. I'm going to say du dx equals 2. All right, now notice that there's a du here. All right, and notice that what I want to do is replace that dx with a du. So I'm going to get this as dx as a subject in terms of du, and let's just see what happens from there. So I'm going to go du over 2 equals dx. Now I'm going to place that du where the dx would go. So that's going to be du over 2. All right, how do we proceed from here? Well, what I'm going to do is rewrite this as integral u to the 3 times a half du. Okay, so all that is a half multiplied by du. All right, now this half can proceed further down here, so just going to change the order. I'm allowed to with multiplication. Half u to the 3 du. All right, and now I'm going to finally use this rule, this handy little technique for integrals, where any coefficient can come out the front of the integral. I'm going to rewrite this as a half integral u to the 3 du. Right, now why am I allowed to do that? Well, I'm just going to show you another case where it works and just show you kind of like, and just sort of go, so you're going to have to trust me from there, but let's just see how it works. If I was integrating 2x dx, I can simply go up by 1, so that becomes 2, then divide by it. So that's going to be 2x squared on 2 plus c, and those cancel out, leaving us with x squared plus c. Or let's do the problem again and grab the constant, or not the constant, the coefficient rather, stick it out the front, and then say that we've got 2, that goes to x squared on 2 plus c. Those cancel out, giving us x squared plus c. Okay, so there's the two same answers. One uses this move here, one doesn't, but we get the exact same result. All right, so let's go over here and do this. So what I'm going to do is write this as a half. This becomes u to the 4 over 4. And with a u substitution at the same time becomes actually 2x takes 7 to the 4, not u to the 4, but 2x takes 7 to the 4 over 4. And we can rewrite that by multiplying it out. So we're just going to go 2x takes 7 to the 4 over 4 plus c for our antiderivative. All right, so there it is with a u substitution. No need for the formula. And if you use the u substitution, you get really, really quick at it. You can do it just as fast as looking at the formula, in my opinion. All right, so here's another example. So what we want to do is integrate 3 over 2x take 1 squared for the independent variable x. So let's do some work on this. So what I'm going to do is get that 3 and pull it out the front, which means that I'm integrating 2x take 1 squared dx. Now I'm going to rewrite that further. So I'm going to use the negative index rule to rewrite this. Terrible x that. And now what I'm going to do is u sub this. So u to the negative 2, and u is equal to 2x take 1 du dx is equal to 2. It's the same derivative as the other example, I think. Right, so what I wanted to do is find an antiderivative of u to the negative 2, and I want to do it for the independent variable u. So I need to make dx the subject, which will allow me to get it with a du in it. So I'm going to go du over 2 equals dx. Let's slam that in, du over 2. Right, now I'm going to do a lot of moves all at once here and see if you can sort of handle this. See? I'm going to rewrite this as 3. Right, now this u will go u to the negative 1 over negative 1, but it's also got this half here, which is going to float to the front here and float to this point here. So this is going to be 3 over 2. Right, multiplied by. Now we've got u to the negative 1, which is 2x to the negative 1 with the u substitution over negative 1. Now that's going to be the same as, so here we go, number of moves in this step as well. I'm going to rewrite this as negative 3 over 2, 2x take 1 plus c for my antiderivative. Right, now what did I just do? 2 times negative 1 is negative 2 rather. So this would be negative 2. The numerator is going to be a positive. So what I'm going to do is grab the negative off the denominator and put it into the numerator. Okay. Right. At the same time, what I've done is grab this portion here, the negative index, and dropped it into the numerator to become positive. So feel free to show a couple of steps in there. But after a while, you'll get the hang of doing a few of these moves. And like I said, it almost will become faster than using the rule, in my opinion. All right. Remember, I looked at this rule over here, so speaking of the rule, and it said you can only use this rule when n is not equal to negative 1. So why can't we use it when it's negative 1? Let's just go back and quickly review that. All right, so what would be the problem of integrating x to the negative 1 dx? Let's try it. That's going to be x to the add 1, which becomes 0 over 0, and oops, we're going to divide by 0 error. Okay, so that's undefined mathematically. So this technique is not going to work for this. All right, well, what we need to know or pick up on is basically anything to the negative 1 is a hyperbola. Okay, so what we're trying to do is integrate a hyperbola. Now, if we backpedal a little bit and think back to differentiation, if you recall, if I've got my original function as log ex, then its derivative is going to be 1 on x. Right, it's on your formula sheet as well, so quickly have a look at that. Hopefully it's pinned up on your wall somewhere or something like that. So it makes sense that if I integrate 1 on x, i.e. if I start with this and try to go back or anti-derive that, I should end up back at my parent function. So if I integrate 1 on x or try to anti-diff a hyperbola, I'll end up back at the log. And then if I differentiate the log, I get back to the hyperbola and so forth. You can go around in circles and keep doing it just for fun. All right, so what we've got below here is the graph of 1 on x, and the other function is the integral or the antiderivative of 1 on x, i.e. log e x plus c. And notice the interesting situation, all right? Now we're used to graphing logs just quickly like that. So that'd be like the standard log e x function. Right, now notice that when I do this, and I'm going to do this on GeoGebra as well, just for effect. So my original function is f of x equals 1 on x, and I integrate that. Come on. Notice what I get is a log here on this side, and also like this side. Now it seems to make sense because, well, this function here has, like, here's my hyperbola, the orange one's the hyperbola, and it has a domain, the set of all real numbers not including 0, okay? So this part would have a parent function and this part would have a parent function, okay? And so the way this integrates it, or what it does, is it shows me the parent function is log e, and it's got these bars here, which means the absolute value of x. Let's ask the same question of the calculator. So I'm going to go edit, clear all. Okay, so I'm going to integrate shift bracket 1 on x. And again, it does the same thing. It gives me these bars here. Now, this officially isn't part of the course, okay? But this, so x means the absolute value of x. Right, so how do I use the absolute value of x? If x is equal to -2, okay, then we're going to get the absolute value of -2, which is 2. If x is equal to 5, then we're going to get the absolute value of 5, which is 5. All it does, the absolute value does, is just forgets the negative. It just says, let's express a negative number as a positive and a positive number as a positive. All right, so essentially what this is saying is the antiderivative is log e absolute value x plus c, right? And you can see what or why this works, because let's just say I've got this value here. I've got 1 that I'm subbing in, right? Now notice what happens is into the antiderivative, this number comes up. Let's have a look on the other side and sub in -1. What comes up? It's the exact same number. All right, so we can use -1, we can use +1, but what I can do is absolute value that -1 and just make it a 1. So the absolute value is -1, it just makes it a 1, and it gives you the same answer in return. Right, so how can you find log ex where x is equal or less than 0, I hear you ask? Well, here's the interesting case here. So again, this seems like it shouldn't happen because it looks like you're logging a negative number, okay? And here officially is what happens on the formula sheet, all right? So what they say is that if you integrate 1 on x, what you're going to get is the log e x function plus c, where x is greater than 0. And the fact is that in methods, x will always be greater than 0, or will always take this positive side here, okay? But let's look at it officially what it is, all right? What we're going to do is if I integrate, so just say my original function was f of x equals 1 on x, right? If I integrate f of x to the independent variable x, the answer is actually going to be log e x, right, plus c, where x greater than 0. That's just by the formula sheet. But also we've got to acknowledge that it's this -1 as well. Okay, so the other one is also and log e -x plus c, where x is less than 0. Okay, so it's got actually 2 parts to it. Okay, or we could write it best as saying let's just sort of try to combine it into one part by saying it's the absolute value of x plus c. So this part here will give us the negative side, but if I absolute value it, it'll just go to the positive side. Right, I think that that's really hard to understand, more so because the absolute value has been taken out of the course, so you're just not familiar with it. Okay, so what I'll try to do is work through the examples and talk through these ideas and try to explain and flesh it out as to exactly how it works. But it's really worth thinking about this and considering it. All right. There's also some rules for anti-differentiation in Cambridge. These are on your formula sheet, so don't use them. Right? Don't use those because this is all VCAR gives you. They just give you that. All right. So let's have a look at this thing. What we want to do is integrate this. Find an antiderivative of it. So what we're going to do is this half here, I'm just going to pull this out the front. So I'm going to write this as a half integral 1 on x for the independent variable x. All right, what do I do? Well, again, the formula sheet says that if I integrate 1 on x, that's just going to be log ex. So this will be a half log e x plus c, where x greater than 0. Okay, now see if you can think about another way that you could write that, or if you can think about what might come out of the calculator. Right, well, if you think that this might come out, you'd be right. Okay, so what the calculator will do is just give you the absolute value version. It's going to allow you to sub in a negative number as long as these absolute values are here. So I'll show you what I mean. So let's go ahead and integrate 1 over 2x. Smart. All right, so that's what the calculator says. So this basically says you can use it for any number in the real number system other than 0. Okay, so I'm going to do the answer with x is equal to 3, and we get this answer. Now, if I did that with mine, we can see here I get exactly the same thing. That's half log e3, right? All right, now this one here, though, so this particular answer, which is perfectly acceptable in 3-4 methods, won't accept values of x less than 0. But what if I put in -3 into the one that the calculator gives me? All right, see if you can think of what might happen at this point. And if you get this right, you are slaying this course. All right, so what I'm going to find here is that we get exactly the same answer. All right, exactly the same answer. Now, why is that so? All right, let's have a look at GeoGebra and it'll tell us again. So let's just change this function here to 1 over 2x. Let's stick some brackets around that. All right, so again, what I did first of all was slammed in 3 into my first derivative, and I got this number here, log, what was it? Half log e3, all right? So we got that. But what I did with the calculator's version is, because it's absolute value, it means that I can put -3 into it, and it grabs this value here, which just happens to be exactly the same value as the one over there. Okay, so to reiterate, you're allowed to use this version here. In fact, I encourage you to use this version here because that's the one that examiners are expecting. But even last year, I was finding that many students would use the absolute value and use it really well. So you can use absolute value. Not too sure what the answers say, but you know, if you check your answers on the calculator, you'll note that you do get absolute value each time. All right, let's try it. So what I want to do is integrate this thing here. So I'm just going to grab that 2 out the front, integral 1 on 2 take 3x dx. Now, what do I do now? So remember that the only thing that VCAR gives us, if my parent function is 1 on x, the integral of f of x dx is equal to log e x plus c, where x is greater than 0. Right, so that's all it gives us. Right, so how can I integrate this thing here? Well, the answer is simple. What I'm going to do is 1 on u, and u is equal to 2 over 3x. Now what that does is puts it into the 1 on x form, except it's 1 on u. So all I need to do is get it with du, and we're all good to go. Now how do I do that? Du dx equals -3. I need to solve for dx. So I'm going to get du over -3 equals dx. Let's just whack that in. U over -3. All right, so now all I'm going to do is take that 1 over -3 and stick it out the front. That's going to be -2/3. Now I'm going to integrate 1 on u, which is log EU. Now the u is equal to 2 take 3x. I'm going to write that as 2 take 3x plus c. Right, now we need to put the restriction in on our derivative. So what we know is that 2 take 3x has to be greater than 0 for it to be able to log it. So that's going to be -3x greater than -2, x less than 2 on 3. So we're going to say where x is less than 2/3. Right, so if you think about it, what this method has done is it's fed us the negative version, or the negative side of the integral. So it'll be like that and that, okay? And what we've got is this side of it, okay? Which is perfectly acceptable. All right, now, is there another way that we can do this problem? Well, yeah, there definitely is, right? So what I'm going to do is clear this and show you another way to avoid going to the left side of the undefined value. All right, so let's do it again. So what I'm going to do is integrate. Let's bring 2 out the front. 1 on 2 take 3x dx. Now what I'm going to do is factorize this denominator here. So I'm going to go 2 integral 1 on -1, which is going to be 3x take 2 dx. All right, now what's that done? Let's just double check that. So that's -3x there. Negative times a negative is a positive. All right, so let's show a few redundant, well, not redundant, but steps that I would shortcut. And see this negative here, I'm going to bring that out further and say that that's -2, 1 over 3x take 2 dx. All right, now we're ready for the u substitution. So I'm going to say that this is -2 integral 1 over u, where u is equal to 3x take 2, du dx is equal to 3, and I need to make this du, so I need to make it make dx the subject. That's du on 3 equals dx, and let's write that in, du on 3. So let's go -2/3, that's equals -2/3. Probably should put some equal signs in here as well, it's pretty bad form. And that's going to be integral of 1 on u is log e, and we're going to do 3x take 2 plus c, where, and let's have a look at that, 3x take 2 greater than 0, 3x greater than 2, x greater than 2 on 3. So where x greater than 2 on 3. Right, so completely different answer to the one we got last time, but in fact exactly the same. Let's see what the calc says. Shift that 2 over 2 take 3x. All right, and what the calc does is it gives you the absolute value, so we could actually rewrite this even further as -2 over 3 log e 3x take 2 absoluted plus c, where x is not equal to 2/3. right? So that gives you the negative one and the positive one. So that negative one would be the same as the first one, but this would be perfectly acceptable, as would the first example, although it would have to say x less than 2/3. All right, so that's tricky stuff there, in particular because there's 3 variations on what would be a totally correct answer. Okay, let's do this one here. All right, so what we're going to do, we'll do this a couple of ways. All right, so I'm going to integrate, bring 3 out the front, and have it as 1 over 2 take x on 2 dx. All right, now I'm going to go 3, 1 on u, where u is equal to 2 take x on 2. That du dx is going to be -1/2. All right, let's process that to get it, get dx the subject. So that's going to be du equals -1 dx. And so I've just cross multiplied there. And then that's going to be du 2 du over -1 dx. Right, so 2 du over -1. All right, now we're ready to go. This is going to be 6 over -1, or -6. This is going to be 1 on u, which is log e. Now u is equal to 2 take x on 2 plus c, where x, or 2 take x on 2 must be greater than 0, -x on 2 greater than -2, -x greater than -4, x less than 4. Right? There's one way to write it. We could also just simplify this or tidy this up a little bit and say that that's actually -6 log e, find a common denominator, which is 4. So that's 4 take x on 2 plus c, where x less than 4. Right, so there's one possible answer. All right, here's another one. All right, so what I'm going to do is just work on this integral just a little bit. So I'm going to say that this is equal to 3, 1 over 2 take x on 2 dx. All right, now what I'm going to do is rewrite this as 3. I'm going to write this as 1 over 4 take x all over 2 dx. That 2 goes up the top and in turn will come out the front. I'm going to do this all in a couple of steps. 6. Now what I'm going to do is same move that I did in the previous example. 6, 1 over -x take 4 dx. That negative goes to the top. 6, -1 x take 4 dx, and eventually ends up out the front. -6 integral 1 over x take 4 dx. All right, now we're ready to finalize this thing. -6 integral 1 over u, where u is equal to x take 4, u dx equals 1. That means du actually equals dx. So we can just slam in a u here. Now that means that it's -6 log e, what was u? It was x take 4 plus c, where you can see that one straight away, x greater than 4. Right, again, perfectly correct answer, perfectly correct answer, perfectly correct answer. Here's one final, one more answer. This is the one the calculator will give you. See if you can write the absolute value version of this. This will be equals -6 log e absolute x take 4 plus c, where x can't equal 4. You could absolute that. You could absolute that. Heaps of different variations on this, okay? So just be careful and be mindful that you might be doing this completely correctly, and when you look in the back of the book or check your answer on the calculator, you might find you get something totally different. Let's see what comes up for this one. What was the original function? It was 3 over 2 take x on 2. There's what the calc gives us, x on 2. It's made a move on that. I wonder what all this will do. Yeah, there you go. So there's another variation on the problem. Okay, so it gives you the absolute of this one, but pulls out the negative from it, which is an absolute value simplify, which really only spec students will know how to do, and I don't even want to go there. So just note that you'd be checking that on your calculator. You'd be like, oh, look, yeah, got this as an answer. And then you type it into the calculator and you get that. Now, how do you know you're right and the calculator's right? Well, put a value into the calcs version, say x is equal to 4. Oh, that was really stupid. It's the only value I'm not allowed to use in the real number system, and I subbed it in. Good one. Right, so that was 8, and when I put that into that, it gave me -6 log E2. All right, now let's do this one. So I've got this, which if you look at it, when I put in 8, I'm going to get -6 log E, and what is 8 take away 6? That's log E 4. Okay, now let's just do it. So I'm going to type in that shift negative, oops, negative 6 ln x take 4 with x equals 8. Oh, that's a can of worms. All right, so let's open up this can of worms a little bit on GeoGebra, and this is pretty heavy stuff here. So anyway, let's get stuck into it. All right, so there is my original function, f of x is. What I'm going to do is get it to integrate it for me. And there's my integral or my antiderivative plotted. So, of course, some logs when I integrate a hyperbola. Now, what did it give us? It gave us exactly the same function that we got down here, except it gave us the absolute version of it. All right. Now, over here, you noticed here that I sort of mentioned that I was going to get a can of worms when I did this part. Well, why am I not entirely worried about two completely different functions returning different values? All right, well, here goes, g of x. I'm going to write or graph the calculator's antiderivative, -6 ln x on 2 take 2. I'm not going to do the absolute version. I'm just going to do the kind of, in inverted commas, right-hand side of the log. Right, so there it is there. All right, now you notice that that's a completely different function. Okay, so I'm not going crazy here. They're completely different functions. Okay, now notice that both of these, when I wrote them as an antiderivative, I write them with a plus c on the end. All right, so what I'm going to do is show you something interesting here. I'm going to add plus c onto this, a constant, right, and create a slider for that. And notice what's going to happen when I put a plus c on this. This constant value here is going to change the graph, all right? So it's going to change the graph. So depending on the constant chosen will depend on how it works out. Now have a look at what happens when I move this constant over. All right, building up the tension a little bit. If the constant is this value right here, right, then it'll produce the exact same antiderivative function as g of x. Okay, so all depends on the constants as well. Right, so all you need to know is, yep, that's a different function. I'm not denying that for a second, but it can be turned into the same function simply by using a different constant. All right, and so that's why this produced this idea here, but it would be correct because the plus c value on either of them would be a different constant, and therefore each one could come out correct. Okay, now that's a real stretch for this one here, and like I said, here, Very, very interesting. Could talk about this example for hours and probably will. Well, I'm going to keep it to, or try to keep it to less than about 10 minutes, but that is an extremely challenging concept to understand. So notice here that I've said here that we've got different antiderivatives, and you'll notice here that often if they're sort of saying that these are the same antiderivative, it has to be for different constants that this happens. So you might find that in some of the answers, I can't remember what Cambridge does, but for some of the answers, they might give you a different C value for both of them. All right. So what we'll do is note that this is a rule. Again, this is the rule that's explained in Mr. Tench's old methods PowerPoints, but also it's in Cambridge as well. But I don't really know what the rule is or how it works, so I'm just going to U-sub it and let's just see how it works. All right, so here we've got this being integrated, so I'm going to say that this is the same as 3 integral 1 on 3x plus 2 dx. Now I need to turn that into a 1 on u, where u is equal to 3x plus 2 du dx is equal to 3, and that's going to mean that dx as a subject is du on 3. And when I sub that in, notice that du will have 1/3. The 1/3 is going to float out to the front, and it will be 3 on 3, which will cancel out the 3. So I'm going to do this all in one move. Integral 1 on u for a du, which is equal to log eu, where u is equal to 3x plus 2, plus c, where x is greater than, what's it going to be, negative 2/3. Okay? Or log e absolute 3x plus 2 plus c, where x can't be negative 2/3. Again, what we're looking at here is two different logs, and we can either take them both. We could say the negative version, or we could say the positive version. That would be the common 3-4 methods answer. All right, last two examples. Antiderivative of this, integral 3x plus 1 over x dx. All right, let's split the x up. So this equals 3x on x plus 1 on x dx. All right, now I'm going to use a cool little move here for the integral. So this rule here says if I'm integrating f of x plus g of x for d of x, dx, for the independent variable x, then I say that this is the same as integral of f of x dx plus integral of g of x dx. All right, so you can sort of think it a bit like the distributive property, okay? But what we can do is just integrate each of the functions separately and add them together, and we get the same result. Okay, so let's do that. So integral 3 dx plus integral 1 on x dx. Don't forget those two dx's there. Right, when I integrate 3, I'm just going to get 3x, and when I integrate 1 on x, I'm going to get log e x plus c, where x is greater than 0. Another variation equals 3x plus log e absolute value of x plus c, where x can't be 0. All right, last example is this one here. Right, so what I want to do is integrate 1 on 2x, 1 plus x. All right, so this is integrating logs, or integrating hyperbolas. This doesn't look like a hyperbola, but this is the classic hidden hyperbola trick. Right, so let's put x plus 1 into 1 take 2x. Now, that isn't the way I'd like to write it, so I'm going to write x plus 1 equals negative 2x plus 1. That goes in negative 2 times, negative 2x, take 2, what's that, 3. So it's equal to -2 plus 3 over x plus 1. So noting that this is really the only time I use long division in 3-4 methods. So that is that dx, which is exactly the same as the integral of -2 plus 3 over x plus 1 dx, which is exactly the same as -2 dx plus 3 x plus 1 dx, which is equal to -2x plus 3 goes out the front. See if you can do this one in your head. So this is going to be 1 on x plus 1 dx. Now that's going to be 1 on u. The derivative is going to be 1. So dx equals du. 2x plus 3 log e x plus 1 plus c, where x is greater than -1, or equals -2x plus 3 log e absolute x plus 1 plus c, where x can't be equal to -1. Okay, again, if you're getting that, that's perfect. That's where you want to be in methods, doing that. Okay, but that's cool as well. Okay, because that allows you to understand the calc output. All right, so there's exercise 11C. Good luck with that, girls.